Hi, and welcome to Lecture 14 in my series on Introduction to Quantum Theory and Technologies. So this week we are going to learn a bit about quantum algorithms. So we're going to put together all the things that we've learnt so far in this course and make a little simple quantum circuit which could run on a quantum computer. As you probably all know, there's a lot of excitement these days about quantum computing, and you can even run small-scale quantum algorithms on devices like I've sort of shown here. So, getting into it. So let's just recap a little bit about what we learnt so far. So what we learnt in the last lecture was that there are sort of elementary gates that we can use, and we learned about sort of one qubit gates, such as this Z phase gate, this X gate, which is like a NOT gate, Hadamard gate, and the C NOT gate. And what we learnt there is that actually you can't just sort of have any old gate when you are thinking about quantum gates, because they basically have to be compatible with Schrodinger's equation, which is like the fundamental equation in quantum mechanics. So the main requirement is that any quantum gate must be unitary, and mathematically that means it satisfies this relation, so that the conjugate transposed matrix multiplied by itself is equal to the identity matrix. So as long as it satisfies that relation, then it should be allowable as a valid quantum operation. So we looked through various types of 1 and 2 qubit gates and found that these ones were compatible. In fact, there are many more types of gates, of course. Particularly for 1 qubit gates, there's not like, there's many more gates that you can actually make. But the point is that by combining some simple set of gates, you can actually make a completely general quantum algorithm just by combining these in a certain sequence and choosing the right types of gates. We can make any type of quantum algorithm, and so this is called universality. Okay, so basically using some small gate set like this, then we can go and combine these and make quantum algorithms. So that's what we're going to basically talk about in this lecture. Right? Okay, so there's a kind of a standard form of writing quantum algorithms. So you can imagine that there's all kinds of different combinations of gates, and there's a sort of a infinite number of possibilities that you could possibly have. But it can actually always be written, not exactly always, but many quantum circuits, and technically those without this so-called feed forward, can be written in this standard form. And so we'll be considering these types of circuits mainly. And so so we'll sort of take this as our sort of standard form of a quantum circuit. So let's have a look at this. So it starts with the initial state, where all the qubits are initialized in the state 0. So presumably the quantum computer can be sort of initialized into some kind of state that you when you want. Then there is the sort of the quantum algorithm. So that's this quantum algorithm that comes in the blue box. And then finally, well, it's no use doing a quantum algorithm and then not getting any information out of there. So of course we want to do a measurement at the end. And so this is the measurement steps that we have. And I've used a slightly simpler notation than what we were using before. I had this little box as the measuring device, but I just cut out the part with the meter and use that as our measurement, denote that measurement. Actually, this is pretty standard notation. So some kind of meter denotes a quantum measurement. And furthermore, I'm going to even say that the measurement doesn't have to be this kind of general measurement that we talked about. Remember, somewhere in the middle of the course, I talked about how measurements could be in sort of different bases. So zero, we don't have to just have a 0, 1 type measurement. We could equally have plus minus or even more complicated different measurement bases. So I'm going to say here that the measurement basis just has to be 0 and 1. Okay, and I'll explain why I can use this sort of what seemingly looks like a specific example as actually a more general framework that sort of captures almost any quantum circuit that you want. Okay, so first, let's just look inside here. So what do I mean by this U algorithm? Because this seems to be the most important part of the circuit. So basically by that, I just mean some kind of combination of these gates that we already talked about. So this is just some random circuit that I just sort of made up. I just put some single qubit gates everywhere and then these C naughts. This is maybe like what a typical quantum algorithm might look like. So it's just a combination of these single qubit gates and these CNOT gates. Right? Okay. So right. So before we talk a little bit about this general form, let's talk a little bit about what kind of rules you can have and you're not allowed to have with quantum circuits, right? So you can't just sort of just do anything with the quantum circuit. We still have to have a few kind of restrictions and conventions there. So firstly, so the gates are applied always sequentially from left to right. So for example, we have this initial state, and in this example of this random quantum circuit, what I mean by that is that I go through and I apply these types of gates in the order from left to right. So this means that on the first qubit, the first thing that I do is apply the Z gate, and maybe simultaneously I apply this C naught gate between these two first qubits, right? Now, as we go from left to right in this quantum circuit, at each point in time, so because basically the time is sort of going from left to right in this circuit here. So at each point there will be a particular quantum state that the quantum computer will be presently in. So, for example, like what I like to do actually with these quantum circuits is kind of draw some kind of dotted line. And this is a bit like, the scroll bar that you have in YouTube or, any video you see on your computer. So just, this is like the progression that you have throughout this quantum circuit. So if I draw this vertical line here, basically at that point, there will be some quantum state that the quantum computer actually is in. So I can move this bar here to maybe here or, any point in the circuit, and then that will have some quantum state, right? And so whenever you want to work out what a quantum circuit does, often what you do is you just work out what the state is at each point. So basically, yeah. So this is sort of the general rule that you always apply these gates in this terms of this diagram from left to right, and basically it always goes left to right. You never sort of go backwards. Second sort of rule, if you like, is that these wires actually, what that really means is that they represent the identity matrix. Right? So as you expect, this wire just kind of transmits or just leaves the qubit as it is, right? So if you've got a state psi here, you put it in this wire, what it does is that it leaves the state as it is. Yeah. So that's basically what the meaning of these wires here are. So at this point here on this qubit, you apply this gate X. Then after that, you do nothing to that qubit for a while. Yeah. And then in the meantime, you might be applying some other gates to some other qubits. Step sort of rule 3, if you like, is that there are no kind of loops, right? So because this circuit is always going to go sort of left to right, we can't have really any kind of diagrams that look like this or circuits that look like this because it's completely ambiguous what that actually means because, here we go, we're going along with our qubit and then we apply this gate here and then we go backwards in time and then come back here. I don't even know what that actually means. So you can't really have these loops like this where it sort of doubles back on itself. This is basically saying the same thing, that you always progress left to right in this circuit and never go right to left. This is different to, you might be thinking, is that a loop of some sort? No, this has a different meaning. This just means that you use, some value on this qubit to influence the state of another qubit. So it's not like this qubit is going, around here or something like that. Qubit is always going on the same line from left to right. This is more like there's some kind of influence that is happening between the second and the third qubit. So the qubit itself is going like this, unlike this one where the qubit is going back in time or something. I don't know. I don't even know what this means. Finally, the number of qubits is always preserved, and in classical circuits, often you don't really. Sometimes you do have things that look like this, and we'll talk about this a bit later. But in classical circuits, often you do have this because actually it's actually very copying the state. This is basically, it means that you sort of copy the state. Turns out in quantum mechanics this is not possible. Talk about this later, but generally, we should always like kind of preserve the number of qubits that we have. So if we start with some number of qubits here, we should end up with the same number of qubits because these are physical atoms or something like that. You can't just sort of be losing atoms or gaining atoms halfway through the circuit. So presumably your quantum computer is set with some number of atoms or qubits, and we don't want to be changing that throughout the calculation. So here, again, this is a bit weird because you've got 2 qubits and you're ending up with 1, or here we've got 1 qubit ending up with 2. Those kinds of things are not allowed. Okay, so let's go back to our sort of generic standard form quantum algorithm that we saw a couple of slides ago, and let's talk about why I can write it in this particular standard form. So in particular, I said that the initial state can always be set to just all zeros, right? But seems like a unnecessary restriction because why couldn't I start with a different state? Then obviously I'd end up with a different state at the end if I have a different state at the beginning. And why can't I do that? Like what's with setting this to be always zero? Well, basically the answer is that I mean, yes, you can, but actually it's still equivalent to the circuit that I drew before, because for example, let's say that you wanted to start the circuit in this state psi. Well, we can always prepare any state psi using another algorithm, like a preparation algorithm, where initially the state is zero. right? So this is some kind of preliminary step that you can do in order to prepare this state psi, and then that psi can go into whatever your algorithm is, right? So that means that what we can just do is basically just join these things together and say that, okay, if I really wanted to start my algorithm not in the state 0, but in the state psi, then I just have this, you know, preparation step here, and then that all together is going to be my quantum algorithm. So basically, even if I wanted to start in a different state, I can just kind of make another quantum algorithm which just starts in 0. Yeah. So basically, then the total circuit is this U prep multiplied by U alg, and that itself is my quantum algorithm, the one in this orange box. Um, so this kind of brings up a little aside. What you might have noted or noticed there is that this orange, U alg was written U alg and then U prep like this. But then when I wrote it with a circuit, it's actually like U prep and then U alg. So, have I messed up here? Why are these things like the opposite order? Here it was, in this order where it's alg and then prep, and then here it's prep and alg. So this is a kind of a common, maybe mistake or a little trap that some people may not realize at first. It's basically just that the quantum circuit notation, so this one, the notation for that is kind of the reverse, if you like, of the mathematical notation. So this one is sort of mathematical notation, and when we write our mathematical notation, we need to have the U prep on the right hand side here, because when we have our combine operator here, and it's going to act on a state, in order for this one to act first, we need it to be on the far right hand side so that this U prep acts first, right? Whereas because the circuit notation kind of goes from left to right, we need the U prep on the far left because a notation is that circuit notation is it goes from left to right. So basically the ordering of these operators is always kind of the reverse between the mathematical notation and the quantum circuit notation. So just be careful of this point because it's a kind of a mistake that some people might make if you're not used to this kind of thing. Okay, right. Again, going back to our general standard form quantum circuit. Okay, so again, a similar kind of question. I said that the measurement can be always just be done in the 0-1 basis. Again, this seems like an unnecessary restriction because I told you earlier that measurements can be done in any bases, right? So what if I wanted to measure in the plus minus basis, or even some other more complicated basis? So, why am I restricting the measurements to be only in the 0-1 basis? Well, the reason is that again, it's very similar to the initialization point. So we can add another circuit at the end here, which I'm calling U basis, and I can basically combine this with the measurements, and the thing in the red box here, I can basically use that as my more general measurement circuit. So I'll tell you how that works in a moment, but if you just believe me for a second, then if I can do that, then again I can just combine this U basis thing here with the algorithm that I wanted to implement, and my U alg dash would just be then this combination of the U alg and this U basis. So this combined thing can be you know, the quantum algorithm effectively where I measure in a different basis. And so the unitary would again be in this reversed order where it's like u alg and then u basis. Okay. All right. So why is it that tacking on some unitary here allows me to measure in a different basis? Okay. So how does that work? Well, you can show this very generally in this way. And it works like this. So remember that any measurement is associated with some measurement operator. Yeah. So this is a particular measurement outcome. It's mn. It's you know, some operator that looks like this. And you know, this n here, what I mean by that is some combination of the outputs here. So maybe it's like I get 0 here, I get 0 here, I get 1 here, I got 0 here. That n here would then be this state here. Okay. So that's my sort of plain old measurement in the 0, 1 basis. So I'm saying that this whole combination here is my more general basis measurement. And so I can just write what that is by just writing it this form. So because this u basis occurs before the measurement, so I need to write the u basis on the far right hand side, then followed by this measurement that I'm doing here. And this mn is this thing in this 0, 1 basis, and this u basis is some other unitary matrix. Okay, and that's my more general measurement that I'm claiming here. Okay. And we can see why this is true because, well, the U basis, you know, this is just some matrix ultimately, right? And so I'm going to write my matrix in this form where these are the matrix elements. And these M's are again in this 0, 1 basis. Okay. And I can just actually rewrite this in a way that makes it clear that this is the general measurement because, well, this combination is a general measurement. I can just put this m dash thing. I can put that inside. Basically, I can combine it with this m dash, this m dash, and then one of these summations. Actually, so this is a double sum that's over m and m dash. I'm just going to put all those three things together, lump them together back here, and I'm going to define this thing called this b vector, and this b vector is defined like this, consisting of the three things that I said: this m dash from here, this umn matrix, and this one of these summations here. And this has got stars because this is the conjugate vector and this is the regular vector. Yeah. Okay. Then now let's put this u thing u as I've defined here, u basis, into this definition, and I'm going to put that m in there. And then what you can find is that actually this mn general is written in this way. So this is n times by some basis n. Okay. Now, if I use this operator and act that on some particular state, and remember, when you do a measurement, what you do is you act, you know, this mn, and I'm going to use my more general measurement here on some state here. And what's going to happen is that this mn is defined like this, and we're going to get a coefficient of bn with this, with this state here. Okay, messed up writing that a bit. But this says bn and this says psi. Yeah. Okay, and then that, for example, we can use that to calculate our probabilities. Remember, our probabilities was equal to something like this psi times by this m measurement operator dagger. This is my measurement operator n, and then psi. And we've got two of these guys. And what this basically will be this bn psi mod squared. Okay, and this n here just becomes becomes 1 because n overlap with n is equal to 1. So this is exactly the probability that you would get if you were measuring in this measurement basis B. Okay, so this basically shows that you can do a measurement in this B basis. And so basically what will happen is that you get some particular outcome 0, 0, 1, 0. But if we've got this big measurement, this U basis thing here, then what that means is that that outcome is not actually 0, 0, 1, 0, but actually the the probability of getting this the nth basis measurement instead, right? So if I didn't have this U basis, then the measurement would just be in the regular basis. But then what I do is if I stick this if I stick this unitary here, then what I get is that that same outcome is now associated with a different measurement basis choice. Right? So this is Bn. Okay, so so basically that shows that so if I just look at this, go back here, that this is actually a perfectly general formulation. It's just that if you wanted to start with a different initial state here, then we'd tack a different preparation thing here, which would be kind of absorbed into the quantum algorithm. If I wanted to measure in a different basis, again there would be some thing that I tack on the end here, which I again absorb into the general algorithm. So this is actually quite a general formulation. I mentioned before that this is okay. It's quite general, but not 100% general. And what is this feed forward thing that I talked about? So this thing is actually something that we'll encounter in the next lecture when I talk about teleportation. But this feed forward is a kind of another step that you can do where, for example, you do a measurement and then depending on what measurement outcome you have, you apply some different gates, like quantum gates, to the circuit later on. So for example, say on the first qubit, say I do these measurements here on the second qubits onward, and say on the first qubit, it was like if I get 0, I apply some quantum circuit on the other qubits, or if I get 1, I apply some different quantum circuit. So depending on if it's 0 or 1, I apply different quantum circuits. So that's what you call so-called feed forward. And so obviously feed forward cannot be written quite in this form, but those without feed forward, you can write completely generally like this. Okay, so so let's have a look at one example of some kind of circuit like this. Actually, this one will not use any measurements at the end. I mean, you can actually add a measurement at the end if you want. That would just basically verify that you've got the state. Practically, when you have a real life quantum computer, what you do want to do is you want to, find what you got at the end of your algorithm, right? So, of course, you want to do a measurement. You don't want to just leave it in the quantum computer. So practically, you would probably always want to do a measurement. But if we're just doing kind of theory, then we know what the quantum state is because we can write it down on a piece of paper. And so doing the measurement is not really totally necessary. Okay, so this is a simple example of a quantum circuit. possibly one of the simplest types of quantum circuits, and this is called the swap circuit. Okay? And the swap circuit, as the name implies, is the aim of this thing is to swap the state of the qubits between these two, the first and the second qubits. Right? So, for example, if I have some state of psi in the first qubit, and if I have another state phi in the second qubit, then by applying these three set of gates, C0 gates here, then what I end up with is the second qubit is on the first one, and the first qubit information is on the second one. Okay, so this is, I mean, this will give us a little bit of practice, basically, in showing how you work out the behavior of certain quantum circuits. Okay, so what we're going to do is go through this step by step. So, as I said before, what I like to do is to draw a little line here, which sort of is like the scroll bar in our quantum circuit, and work out what the state is at each point in the circuit. Okay, so the first time that we can just write down is just immediately after the initial state. So in this case, like I've said before, if you like, I could start with state 0, 0. There could be some some gates in order to initialize this. Again, I'm not going to really, I'm not going to write that, but you can consider that that's sort of already being done. Okay, so at this point, you have these states psi and phi, and suppose they're just defined like this. So at the initial point here, point of this red line, the state of the quantum computer is psi times phi, which I've defined like this. So I'm going to multiply it out. And so each of these four terms have coefficients like this. So alpha gamma, alpha lambda, and so forth. Okay, so that's our kind of initial state. So let's apply our first C0 to this. Okay, so I take my state here, which I'm calling T1, so time T1 if you like. Our state T1 is the state where I've taken my state here at T0, that's my initial state, and I apply my C0 gate. And the C0 gate is not totally symmetrical, so you need to actually specify, like, which one is like the control qubit. Remember, the control qubit is this one with the black dot, and the control knot, if you remember, just to recap, what it does is that it, depending on the state of the control qubit, which in this case is the first one, it will flip the state of the second qubit. This is it's called the target qubit normally. And it flips it if the control qubit is 1, then it flips it. If the control qubit is 0, then it will do nothing. Okay, so that's the signal. Okay, so you could do this with a matrix form, but I find it actually easier just to even write it out in this form. So here's our state that I wrote from the previous slide, and I'm going to apply my control knot, and basically I just follow that rule which I just said. So here's the first qubit is our target qubit. Control qubit. First qubit is a control qubit. Second qubit is our target qubit. That's the one that flips or doesn't flip. Okay, so this one is control qubit 0, so we're not going to do anything to this qubit. Okay, so that one stays as it is. Control qubit is 0, again, we do nothing. Control qubit is 1, so we flip the state of the second qubit. So that's why this term turned into 1, 1, whereas these other terms remain the same. Okay. Similarly, over here, the control qubit is 1, So the target qubit, we have to flip that. Okay, so 1, 1 became 1, 0. Okay, so that's our state at this point here, T1. All right. Okay, so we just basically continue this process and work out what the state is at each point. So let's now apply our second gate here, T2. Okay, T2 is, of course, you apply the control knot to the state T1. That T1 is the state that we had before. And notice here that the control qubit is actually on the second qubit, not the first one. So we have to apply our controlled knot rule in sort of the opposite way, where the second qubit is the one that is going to determine whether the first qubit flips or not. Okay, so here's our state from the previous slide, and we're going to apply our controlled knot with the control qubit on the second qubit. Okay, so second qubit is 0, so we do nothing on the first qubit. Second qubit is 1, so we've got to flip the first qubit. So that's why this one turned into 1, 1. This 0, 0 remains the same. Second qubit is 1, so we've got to flip our first qubit. So it becomes 0, 1 from 1, 1. Second qubit is 0, we do nothing on the first qubit. Okay, and now down to our last one. So we do the same thing. So here's our state from the previous slide. Now we do our sort of the C knot like the first one, where the control qubit is on the first qubit. Okay, so here first qubit is 0, so we do nothing on the second qubit. Here first qubit is 1, so we flip the second qubit. 1, 0. Here first qubit is 0, do nothing on the second qubit. Here first qubit is 1, we flip the second qubit. Okay, so here's our final state that we got at the end. Okay, now we want to see that it's really swapped, because that was the aim of this whole circuit, right? So let's do a little bit of factorization. So here on the first two terms, we can factorize out this second qubit here, because it's both 0, right? So the second qubit is always 0. Whenever you do these factorizations, you should be always careful that you don't mess up like the ordering of these two qubits. So if you've ever got it so that it's like 0, 0, okay, 0, 0 doesn't matter, but if it's 1, 0, you should always make sure that the 1 is first and then the 0 is second. No matter what factorization you do, you don't want to have it so that, like the 1, 0 becomes 0, 1, because that's a totally different state. Okay, so I'm going to factorize this such that the second qubit is always the second qubit. So here the second qubit is 0. So I'm going to factorize that out carefully so that the so that basically this thing is always it's out here on the right hand side. I don't want to put it here on the left hand side. The ordering here is a little bit important. Okay, so I factorize this out. I could also factorize out this alpha term. The alpha is just a number that can go anywhere. So I can put that at the end, middle, whatever. Doesn't really matter. Okay, I do the same thing here. Second qubit is 1, so I'm going to factorize that out here. And I'm going to put it on the right-hand side because I don't want to mess up the order. Again, the beta also factors out. Okay, and then now this thing here is the same as this thing here. So I can, again, do a second layer of factoring where I factor these two guys, and they're both on the first qubit. That's why I can really factor it out. So then this leaves, on the second qubit, it's alpha 0 plus beta 1. Remember, you have these coefficients here. Okay, and now if we compare that to our initial state, so this thing here is our phi, so that's on the first qubit now. And this thing here is our psi, that's on our second qubit. Remember, we started with psi on the first and phi on the second qubit. So swap is accomplished, and we've basically shown that this indeed swaps the state of the two qubits. Okay. All right. So Now you might say, well, what if I start with a more general state here? We don't have to have two states which are, psi and phi. What if these are even entangled or something? And the answer to that, and I believe this is one of the homework questions, you can actually work through this yourself. But basically, you can still apply the circuit to it. It just because the state is entangled, it doesn't really, you know, swap the qubits in this case. But it still does actually swap the identity of the qubits. So if, for example, there's this qubit, the state of this qubit and this qubit is sort of asymmetrical in some way, it will still swap the qubits. So it's in the same state, but then kind of the labeling is reversed. Anyway, I think you'll see this more in the homework. Okay, so we talked about the swap gate. So this sounds like a pretty sort of elementary type of thing that you might actually use in larger algorithms. You can use swapping to shift around information in the quantum computer. So imagine as our quantum computer here, what we can do using our swap circuit is to kind of move around qubits. Well, informationally. So of course, physically, the qubits are probably completely fixed in the quantum computer. You don't want them to be moving around the place. So instead of physically moving them, we can actually just move the information that is encoded in them. And because these qubits are basically nearly identical, this actually achieves pretty much the same effect as physically swapping them, right? So physically swapping the information is basically equivalent to swapping the physical realities of these qubits. Okay. Now we might think, okay, well, we've done swap. Let's do possibly even more useful circuit, which is the copy circuit. So copy paste is obviously one of the most wonderful things that computers can do, right? Copying stuff actually is basically done for free in quantum in regular computers, and this is why a lot of these things algorithms are so powerful. So we'd like to do something like this in the quantum sense too. So let's try and work out whether we can do a copy circuit. Okay, and it's often useful to get inspiration from the classical circuit. So let's have a look at how you do a copy circuit in the classical world. All right, and actually the copy circuit can be done with the so-called OR gate. So we met the OR gate, I believe, in the last lecture. And what you can do is use that kind of slightly modified OR gate because the regular OR gate has like two inputs and one output. And obviously, if we want to copy something, we don't want to be losing one of them in the process. So let's sort of kind of send this guy forward so that we use this guy as one of the outputs and the output of the OR gate as the other output. Okay, and as the input, we're going to have the thing that we want to copy. So that's X. That's the thing that you want to start with. And the other one, we're going to initialize just to 0. And if you work out what the OR gate does, so remember, OR means that if one of the inputs is 1, then that's good enough. The output is also going to be 1, right? Remember, the guy that wants to go to the beach, he goes to the beach either if he's got a day off work or he's in good health. Either one, he'll go to the beach. Right? Of course, if both are 0, then the output is 0. Okay, so the input, the first one, which if this one is 0, then and the input of the second one we've always set to 0, then the output is going to be 0 because 0 or 0 is 0. In the case that it's 1, 0 or 1, remember 0 or 1 is 1, so the output is 1, and this that's this one, and this guy here is just the same as the initial state. So so basically now, if this is x, so if this is x, then we basically get exactly the same result on the output here. So because the input is 0, 1, and the output is 0, 1, we've got exactly the same inputs and outputs, and so this achieves a classical copy. Okay, so how do we make a quantum version of this? Well, what we might try is something like the C0 gate. Okay, so actually C0 gate is something pretty similar. This control qubit is a bit like this first one, which sort of controls the nature of this second one. And if we always initialize this second qubit to 0, then we can work out that the second qubit basically gives the same relations as my OR gate. So in the quantum notation, sort of looks like this. Okay. So let's just try the same cases that we had in the classical case. So for example, if this initial state here is 0, then according to our C0, remember this is our target, and this is this is control, and this is a target. The control is 0, so we do nothing on the first qubit. Okay, 0, 0. And if this guy is 1, then on the second qubit we flip it. Okay, so we flip the second one because this one is 1. So we flip it, now it's 1. Okay, well now looks like started with 0, here's 0, 0, 0, started with 1, here's 1, 1. Okay, it looks good. This looks like we've got our quantum version of the copy circuit. The only problem here is that actually that's the only cases that it actually works. Because remember, of course, quantum mechanically, we don't have to just have 0 and 1. We can have some other state like alpha 0 plus beta 1. Okay, then if we apply our C0, then we get alpha 0, 0 plus beta 1, 1. Okay, because again, this is the control qubit, flips it if this is 1. So in this combination 0, 0 does nothing. This combination 1, 0, it flips it. But actually, this state is not what we really want. What we actually wanted was that this state to be psi, psi, right? And if we compare to what we actually wanted, which is psi, psi, psi times psi, this state is actually alpha squared 0, 0, alpha beta 0, 1, alpha beta 1, 0, beta squared 1, 1. That's actually not the same as this, right? So in general, the C0 gate is not a copy gate or copy circuit. It only kind of works in these two particular cases, which actually coincided with the classical case. Okay, so have we messed up? Is there a different circuit that we can write down? Actually, it's impossible to make a circuit that actually copies a qubit. So you can swap a qubit, you cannot copy a qubit. And this has a very famous name called the no cloning theorem. So let's see why this is, or let's write down a proof of why this is. So we're going to do this by contradiction. So suppose there's a circuit such that it achieves the thing that we want. Okay, so what we're going to do is we're going to first suppose that we're going to write some circuit, and if we get some nonsense at the end, then uh, uh, that means that our assumption was impossible. This is proof by contradiction. Yeah. So yeah. So okay. So here's our hypothetical copy circuit, which achieves the thing that we want. We have some state here, phi. We initialize that state to 0, and at the end of the copy circuit becomes phi phi. Now this could actually have some kind of funny phase here. That's totally fine because we don't, if you remember, this is a global phase, and in quantum mechanics we don't really care about global phases. They don't really do anything, so it can be there, doesn't matter. Now, what we're going to do is we're going to compare two instances of states that we're going to copy. So here's phi dash, which is some different state. Okay, and let's just write down what this quantity phi and phi dash is. Okay, and phi inner product with phi dash is some number, whatever. Depends on what we chose, but it doesn't matter what it is. And let's just introduce a factor of 1 here. This thing here is actually just equal to 1. Yeah, 0, 0. Okay, and I'm just going to rewrite this part here because this is my conjugate vectors. So I'm kind of introducing a second qubit here. So this was for just like 1 qubit, and now this is 2 qubits. And because this is actually equal to the inner product between these 2 qubit states. So here's phi 0, and that's my uh, conjugate vector, 2 qubit conjugate vector. Here's phi prime 0, that's my regular 2 qubit vector. And because this circuit is supposed to be, any quantum circuit is a unitary circuit, and a unitary circuit always satisfies u prime, u dagger u is equal to I. So this stuff here is equal to I. So I can just always introduce that in the middle there, and shouldn't change anything. Okay, now I've done this because now I can now use my assumption that I claimed at the beginning here. Okay, so according to this, you copy. What that does is when it acts on this phi and 0, it copies this one so that the second one is phi prime. This thing is just the same thing, but just a conjugate vector of this. So because this whole thing can be written as, so this part of this expression, so this part is just the same as you copy of phi and 0, and then I just take the dagger of that whole thing. And then so that thing, I can use that expression there, and this thing is going to be equal to basically the dagger of the right-hand side here. So that's going to be e to the minus, and remember dagger, you always have to flip the sign of i's. So there's an I there, so we've got to flip the sign of that. And these guys are phi and phi. Okay. All right. So that's that stuff there. This stuff here is similar, but it's got phi prime. And if I take the inner product between those two, then I'll get some phase factor, which is a combination of this one and this one, and the square of phi overlap with phi prime. Okay. So what I've got here, if I compare with what I started and what I end up with, I got phi prime is equal to the square of phi prime with now this factor here, phase factor. Now, this phase factor is a little bit messy, so we can actually just get rid of it by just taking the modulus squared. That means, remember, multiplying by the complex conjugate, A times A star is the definition of complex conjugate, A mod squared. So what I'm doing here is I'm taking the conjugate conjugate equation here, multiplying it by the original equation, and I get this. Okay, now what I find here is that phi over phi inner product phi prime modulo squared is actually equal to phi of inner product phi prime to the 4. Okay, so this is like saying, x. If I say that this guy here is x is equal to x squared. Okay, now x is not equal to x squared. Well, it can be. It's true if x is 0 or if x is 1, but basically it's not true any other time. So basically, because I started with this, this is basically saying that this is only really true if these if the phi and the phi prime is actually equal to 0 and 1, but that's not a general case, right? I could choose a phi and a phi prime with the inner product, which is not those numbers. So that basically shows that it's, our original assumption must be incorrect. It cannot be a general statement. Okay. So the cases that actually did work out, it so happens, coincide exactly with the cases that I got my hypothetical copy circuit to work. So remember, this actually did work for these two cases. In fact, this kind of proof shows that those two cases also are the only ones that work. So, so that basically shows that it's impossible to have a copy circuit. And as I said, this is called the no cloning theorem. And interestingly, this was discovered only for the first time in 1970. Okay, so 1970 sounds like a long time ago, but if you consider that quantum mechanics has been around since really the beginning of the 20th century, and basically there was a full theory already in the 20s or 30s. So it took really quite a long time for people to realize that you cannot do this, and and this is not like a super complicated sort of result. Even the proof is pretty simple, really. Physics proofs can be really very long. Comparatively, this is really quite a simple result. In fact, it was sort of rediscovered by these guys here in 1982, and they even got a Nature paper out of it. So, well, why did it take so long for people to realize this? Well, it's basically because of what I mentioned maybe a couple of lectures ago, that people didn't really have this mindset of quantum states being a kind of information, really. So, really in the early part of quantum mechanics, people really just, were describing physical objects and, like atoms and, crystals and things like this. They weren't really thinking like, can you control the system and make the system in whatever quantum state that you like? And because people are not really in that mindset, copying something is obviously some kind of active process that probably a human is doing, not some law of nature. So that's why nobody really thought to look at it. So it's kind of interesting that if you've got the wrong sort of mindset, then you don't discover these sort of fundamental results. So it's kind of incredible how recent really this result is. It also is interesting because it shows you that actually making quantum circuits is quite difficult in general. So the kind of things that you naturally would want to do, such as this copying, some things are just simply not possible with quantum circuits. So it's not really as if you can just do absolutely anything with the quantum circuits. You really have to keep in mind, what is sort of allowed and what is actually physically possible with these quantum gates. So this sounds like, this quantum circuits are sort of more restrictive than classical circuits, but actually this is not true. Um, as we saw here, over here, doing the classical uh, version of the circuit in quantum mechanics is always possible. So you can actually always do this. So this is not like a special case. If you wanted to do some classical sequence of operations, there's always some quantum gates that could do basically exactly the same thing. It's just that when we try to do the uh, kind of quantum versions of the same types of things, this is where some things become not possible. So if we write all the possible classical algorithms that we can have, kind of as this set here, this orange set, then quantum algorithms basically are an extended set of algorithms over that, because you can always use some quantum gates to do the equivalent classical operation, right? It's just that the quantum algorithms will have extra things that you might be able to do, and basically the question in quantum algorithms is really, so what useful things can you do with these extra steps? So um, with this extra power that you have of basically superposition and entanglement, what more can you do with the quantum algorithms? And this is something that people are still really investigating and researching, well, finding quantum algorithms is useful quantum algorithms is actually still a major topic of research. Okay, so I think we'll leave it at that today. Please, I've set some homework questions in order to get you used to working with these quantum circuits. So please go through that. And next week we will go on to talking more about quantum circuits, and we'll talk in particular about sort of teleportation and things like that. Okay, so thanks for listening, and see you next lecture.